Racing is as much an engineering and physics problem as it is a sport. From race car design considerations like the engine, tires, and suspension, aerodynamics, the role of friction in the vehicle's interaction with the terrain, and making driving decisions, almost all of racing ties back to physics principles. Many race car drivers have an intuition and may not think about what they're experiencing racing in physics terms, although understanding the physics of driving can make you a better driver or enjoy watching racing more. As a math magician, or a person with a background in physics and a deep love of overanalyzing magical media, let's break down the physics behind the racing vehicles in the new Magic the Gathering set Aetherdrift and see if we can use physics to evaluate how the vehicles will fare during the race. In the Aetherdrift story, a previously underground race becomes a government-sanctioned event, the Girapur Grand Prix, where the prize is an Aether Spark. We see a lot of characters and cards, and with so much on the line, everyone is out to win. There are two elements that we're going to consider: the aerodynamics of the design and the interaction of the vehicle with the terrain. There are some incredibly cool race cars in this set, and the design of the car has an impact on its speed. To understand the design of these cars, we need to think about aerodynamics. Aerodynamics is the study of the properties of moving air and the interaction between the air and solid bodies moving through it. As a race car moves quickly, the way that the air moves around it is an important consideration. And so, vehicle aerodynamics is a major design parameter when building the body of the vehicle. If we want to speculate about which racer in Aetherdrift is the fastest, we want to look at how the shape of the car will interact with the force of the wind as it drives forward, and consider what design factors of these vehicles will introduce or minimize drag, lift, and side forces. The vehicles in Aetherdrift have complex geometries. The aerodynamic interaction between the various body components would be significant and would likely result in vortex flows and lifting surface shapes, unlike traditional airplane wings or cars. In race car design here on Earth, methods that generate negative lift or a downforce have been shown to increase race car performance. And as we consider the racing vehicles in the Girapur Grand Prix, we can look for some of these techniques, such as inverted wings, diffusers, and vortex generators. As I was looking through the cards, I noticed some that had details that definitely wouldn't help. This sail on boosted sloop, that would just catch the wind and slow it down. But it is a really beautiful card, and the notion of sailing through the wind is cute, albeit impractical in this race. Typical design tools engineers and physicists use when designing race cars are wind tunnel testing, computational fluid dynamics, and track testing. I don't think any of the racers will lend me their vehicles, so let's use some computational fluid dynamics. We're going to use the Open Foam Solver developed by CFD, along with the Model Builder application from Kitware for this computational fluid dynamics investigation. We're going to be using the simulated wind tunnel to look at how some of these designs fare.
We're going to look at three vehicles. First, we have the Hull Drifter. The artist Juan Marquez depicts this snazzy ride as a sleek hover vehicle with a sloping chassis and 8 large thrusters. I modeled this one from scratch in Blender, trying to capture the basic shapes of the vehicle. Next, we have the Midnight Mangler. This piece by Boneface is so metal. Huge exhaust pipes on a super cool hot rod with a massive skull for a front end and a flying V guitar sticking out the top as a hood ornament crown thing. This one I put together as a sort of Frankenstein of a hot rod car, a skull, and a guitar I found on free 3D modeling sites. Finally, we have our real world vehicle. This motorcycle is from the Open Foam Demo Library. This model has been analyzed to death by countless engineers, but it also looks strikingly like Chandra riding her motorcycle, so it's relevant to this investigation.
From the cars here on Earth, we know some ways cars are designed to improve their aerodynamics. To reduce drag, car designs are often streamlined minimizing parts that stick out. You might have noticed that race cars don't have mirrors like street cars do. We already have a bit of an intuition based off of our interaction with street cars about ways that cars are designed, and we can use this as we approach this simulation. The magical components of these vehicles add additional variables that extend past the parameters of this video. With that, let's dive into the simulation.
For our analysis, we'll be using OpenFOAM, the finite volume solver, to simulate flow of air around these vehicles using a virtual wind tunnel. To do that, we need to create a finite volume mesh by cutting the wind tunnel into thousands or millions of little hexahedra on which the solver will compute a solution to the governing physics equations of fluid motion. We can do this sort of automatically here. Next, we set the wind speed coming into the box. Since we're looking at racing vehicles, we're going with 70 meters per second, which is in the ballpark of how fast race cars on Earth drive. CFD can take a pretty hefty toll on your computer, so we are only simulating a very short duration of fluid flow, maybe 0.1 seconds total. Even so, we'll need to compute around 2,000 time steps for that short duration of physical time to properly resolve the fluid dynamics. This would not be enough for a proper engineering analysis, but we're looking for ballpark comparisons here. Now we hit run and wait. First off, let's look at pressure distribution. Already we see on the Midnight Mangler a high pressure across the skull and guitar. Totally unsurprising by intuition. The large flat surfaces will have to move a lot of air out of the way as the car drives forward. We see a bit of high pressure along the front of the whole drifter, but as expected, the sleek design allows air to flow around it more smoothly, leading to less high pressure regions. This is similar to our motorcycle. Next, we can compute streamlines, which trace out the path air moves around the vehicle. Again, for the bike and whole drifter, we see smooth paths traced along the bodies of the vehicle. But for the Midnight Mangler, we see kinks and sharp turns where the air needs to deflect around parts of the vehicle. We expect vortices to form behind these corners. Vortices, or spinning fluid, take energy to produce, and that energy would come from the vehicle moving, ultimately sapping energy away from making the car go faster, which is kind of the whole point.
Another physics consideration for the races is the car's interaction with the terrain. Tire characteristics are a huge consideration with race car design, and for our discussion, we'll need to consider both the tire design and the hover technology utilized in this race. In a race, the straight lines are typically considered the easy part. Everything happens in the turns. It boils down to the grip of the tires on the ground and ultimately who's the better driver. Racing is about bringing the speed of a car down for a turn, turning and re-accelerating out. The Gyropur Grand Prix passes through multiple planes. These transitions and turns will likely be the points that will make or break a racer's performance. It all basically boils down to the grip of the tires on the ground, because throughout the entire turn, you need to stay inside the maximum grip. Otherwise, you'll lose control and the car will not steer where you want it to go. Unlike when a person is driving a car normally, when you're racing a car, you want to continue going as fast as possible for as long as you can and then minimize the time you're in the curve. This means that you are full throttle on the gas up until the moment you need to turn, the last possible second. Drivers typically map out the potential path through the curve. These are called drive lines. They want to make the biggest circle within the turn, but turn in a little earlier so they can have the straightest possible path out of the turn. So the goal is to consider what drive lines would be the fastest while maintaining grip. The ideal drive lines varies depending on factors such as the sharpness of the curve, track conditions, and the vehicle's dynamics. There's tons of variables to consider, but here in the Gyropur race, the tires I think are going to be one of the biggest considerations because the track will be the same for every driver. It appears that each of the different teams in this race utilize their own wheel design. Let's look at two different designs and consider the pros and cons. Race cars on Earth often have smooth tires, also known as slick tires, to maximize traction on dry raceways. This design allows for more rubber to touch the road, which improves acceleration, steering, and braking. It looks like a lot of the Aetherdrift cars utilize some of this slick tire design. Some examples are the light wheel enhancements and the Cloudspire Sky Cycle. But even the Insects car designs, while they're much more round and bulbous, still look like they have some slickness or flatness to give them more traction on the raceway. These slick type of tires would perform well on a racetrack, but if there are changes in the track or inclement weather, they might run into some trouble. I also noticed that some of the race cars have really spiky tires. Some examples are the Explosive Getaway for the Duskmorn team and the Prowcatcher Specialist and the Boom Scholar for the Goblins. The tread pattern of these tires played a role in determining their friction and skid resistance. On a paved road in dry conditions, smooth tires have better traction, but as there's no guarantee that the track in the Ghirapur Grand Prix will always be dry pavement, these spikes might come in handy. While we can't know with certainty how each team designs their individual vehicles, we can assume that many of these hovercrafts float above the ground by riding on a cushion of air that's generated by lift engines. Rather than designing the vehicle in a way to minimize this turbulence, like the race cars that utilize wheels might, they would need to embrace the airflow. This lift would be impacted by both the aerodynamics of the vehicle and the distance and interaction with the surface of the track. They would have a lot more to consider in their designs. But the vehicle design, the racetrack, those are only part of what goes into racing. Drivers have intuition on many aspects of racing, even if they don't know all of the physics. While we can use our knowledge of physics to look towards some of the driving decisions that these racers will be making and how that will impact their success, the driver ultimately does have such an impact on the success of the race. The only way to know the outcome is to read the Aetherdrift story. Thank you, Wizards of the Coast, for sponsoring this video. Aetherdrift is available now at a game store near you. The cards are absolutely stunning. I'm obsessed with this Redshift card. I desperately hope to open one. It's moving away from you so fast it looks red. Redshift is a phenomenon in physics that occurs when light waves stretch, causing them to appear redder. It's a result of the Doppler effect, which happens when the source of light is moving away from an observer. Literally such a great physics Easter egg in this set. And thank you so much for watching. If you want to keep using science to analyze Magic the Gathering, I have another YouTube video where I run over 1 million simulations to determine if poison counters are overpowered. You can watch it right here.